Hi everyone, welcome to ML Summer School. My name is Pranita Khandelwal. I'm a senior data scientist in the international machine learning team here at Amazon. I work primarily on buyer abuse prevention and payment experiences. Today, I will be taking you through session 3 of our series on causal inference, where we will be deep diving into different causal ML methods. But before we get started, here's a quick recap of what we have previously covered. So, in part 1 and 2, we've looked at the motivation for causal inference and discussed that while supervised learning excels at prediction, causal inference helps us answer questions like what will happen if we take a particular action. We looked at a few core concepts of causal inference. For example, what is the distinction between correlation versus causation, and how observational associations can be misleading in the presence of confounders and selection bias. We also understood the notion of counterfactuals and what it means to intervene on certain variables rather than passively observing them. We discussed a few causal questions of interest. For example, how do you determine the causal structure and cause and effect relationships given a set of variables? And how do you attribute the impact to causal variables? What happens if you intervene on the data generating process? And how do you reason about the what if questions or the counterfactuals? And finally, based on the treatment effects that we estimate, how can we learn optimal policies for treatment assignment that will help us maximize rewards? To answer these causal questions of interest, we looked at a few frameworks for representing and reasoning about these causal questions. One such framework is the potential outcomes framework, which provides us with the notation for expressing and defining causal effects using counterfactuals under treatment assignment. So essentially, it helps us write these causal queries because there exist no mathematical operators as such to denote causal objects of interest. Next, we looked at the structural causal models, which express causal relations in terms of structural equations between variables. And these help us reason. This framework helps us to reason and about the interventions and the counterfactual outcomes. Another complementary framework to SCMs is causal DAGs. So this is a way of visually representing the causal relations in a graphical structure using probabilistic graphical models that encode the joint probability distribution over the variables. And in the graph, the edges then denote the flow of causal influence between nodes. So these causal DAGs encode the qualitative assumptions about the data generating process. And we also looked at concepts like deseparation, which allow us to factorize this joint probability distribution more efficiently and enable causal reasoning. And finally, we looked at do calculus, which operates on this graphical structure. And do calculus offers us a set of rules that help us determine that given any causal question or causal query, can that be answered using the observational data that we have. And these rules help us identify which variables we need to adjust for and how to go about the estimation of the data. So, right. So basically, we've looked at a few frameworks that counter help us map causal queries into statistical estimates that can be estimated from the data that we have. Next, we looked at uh, randomized experiments and how they are considered the gold standard for conducting causal inference. Because the treatment assignment is randomized and we don't run into problems that we do with observational data sets, um, where confounding can be a big problem. Uh, we then looked at identification assumptions. So given observational data sets, if we want to make causal effect estimation possible, then several assumptions need to hold, which include sattva, unconfoundedness, overlap, and consistency. So if these assumptions are getting satisfied, then we can be confident that our observational data can help us answer those causal questions. And finally, we looked at a few classical methods for estimating average treatment effects, like matching, stratification, inverse propensity weighting, and augmented inverse propensity weighting. So, with that recap, let's move on to the focus of today's session. As datasets become larger and higher dimensional, some of the classical methods like matching and stratification start struggling um, because in higher dimensions, the curse of dimensionality sets in. This is where modern ML methods can be quite helpful because first, they do not impose any rigid parametric modeling form. They're quite flexible and they can estimate complicated treatment responses and statistically and can be used to estimate unbiased, statistically efficient estimates of causal effects. And in this session, we will focus on the following core topics. What are heterogeneous treatment effects, and how do we go from average treatment effect estimation to heterogeneous treatment effect estimation? These methods, these uh, these allow us to answer questions of not just what is the average effect over a population, but also inside that population, which are the units that benefit most and by how much, and how these benefits vary. We will look at the evolution of causal ML methods from meta-learners, causal forest to deep representation learning methods and the intuition behind uh, each approach. We will also look at focus on orthogonal and doubly robust machine learning and introduce concepts like Neyman orthogonality and cross-fitting. And finally, we will look at the frontiers in causal machine learning and look at emerging research directions and applications outside of treatment effects estimation. With the agenda out of the way, let's move on to the topic of today's discussion, which is the estimation of heterogeneous treatment effects using causal ML methods. So far, we have looked at the estimation of the average treatment effect, or AIT, which answers the question, on average, what is the impact of a treatment? Or in other words, what happens if I apply a certain action? It is defined in terms of the notation that we saw while studying the potential outcomes framework as the expected value of the difference in potential outcomes when a unit is treated versus when it is not treated. But tau by itself is not sufficient if we want to answer questions like who benefits the most from the treatment and how should we assign the treatment policy that would maximize some outcomes. So to do that, we need to become more granular and we define heterogeneous treatment effects or the conditional treatment effects, which is a function of the covariates. Given a set of covariates that we care about, we define the tau of x as the expected value of the difference in potential outcomes conditioned on the covariates. And tau of x is related to tau uh, in the sense that if you marginalize over all possible x values, you would recover tau. So this is noted here. If you look at the figure on the left, it shows the same motivation for moving towards gate. Uh, if you had a homogeneous population, in that case, the unit level treatment effects would be very similar to the ATE. But in most real life cases, we run into cases where the treatment effects can vary considerably across the units. And therefore, if we want to identify who benefits most from a treatment, we need to move towards gate. So one example of this is, of course, in precision medicine, where if you do a population level study, you might be able to find that a certain drug benefits patients in, let's say, reducing blood pressure, but it doesn't tell us who are the patients who benefit the most and if there are any patients who actually are harmed. So to answer those questions, we need to estimate Kate. Let's look at another example. Suppose you are a marketing manager and you want to drive higher order conversions on your website. And given the list of customers and their buying propensities, suppose you're also able to get some estimates of their treatment effects if they were offered a coupon. Who do you think the marketing manager should assign the coupon to, given these values? So take a pause and think about it. Okay. So if we see the four customers, we see that Charlie has the highest probability of purchasing, and assigning them the coupon only increases the incremental conversion rate by 1%, which so it's not really moving the needle much. Whereas if you look at Alice and Bob, who both have a buying probability of 60%, giving a discount offer um, drives Bob towards higher conversions, and therefore we should ideally be assigning the discount coupon to Bob because it is driving the highest incremental change in the order conversion rate. Another example is from policy learning. Suppose we have learned the key estimates and we are now interested in learning the decision rule that will help us determine who should get the treatment assigned. And suppose we are in a scenario where there are resource allocation, where we need to do resource allocation due to budget constraints. And suppose the cost of assigning the treatment itself is C. So anytime you assign a treatment, you incur a cost C. So in such scenarios, what we might want to do is, target only the top K most promising customers whose benefit exceeds the cost. So this is denoted here, where we would uh, rank all customers or units by their conditional average treatment effects and only assign the treatment to those units where the expected treatment effect is higher than the cost. So the cost is denoted by the dotted line here, and all units um, for whom the estimated Kate is more than C, these are the ones we would want to target. So moving on, we have looked at how to define Kate, but now the question is how do we estimate it? So if you look at the previous equation, we expressed the definition of Kate in terms of the potential outcomes. But as we have seen before as well, the fundamental problem of causal inference is that we only observe one outcome per individual. So we only observe the treatment outcomes from the treatment that was assigned and not the counterfactual. So then how do we translate that causal query to a Kate estimate? So in such a scenario, we have a workaround. So suppose we have an observational data set, and if the following causal assumptions on the right are satisfied, which are Satwa, which says that there is no interference between units, and the observed outcome equals the potential outcome under the received treatment. If we have no unmeasured confounders, which says that conditioning on all confounders ensures that the treatment assignment is randomized, and the probability of a unit getting assigned to the control or the treatment is random. And finally, we also have the condition of positivity, assumption of positivity, which states that the probability of getting either treatment is more than zero, so that there is sufficient support on both the treated units, so that we have sufficient units that have been assigned both to the control group as well as the treated group. So if these causal assumptions are satisfied, then we say that the causal query expressed in terms of the potential outcomes can be expressed in terms of a statistical expression and estimated using the observational data that we have. So then tau of x then reduces to um, this expression where mu is the expected value of y given X and T. So the mu, or the conditional outcome, can be estimated from the data. And in this section, we are going to see that this estimation is done using flexible ML models, which are really good at doing this kind of prediction. So moving on to the next section, which is estimating Kate using meta learners. So far, the methods that we saw for estimation of average treatment effects, they were using classical techniques like linear regression for outcome modeling and logistic regression for propensity score modeling. But as the data sets get larger and higher dimensional, then the treatment effect estimation gets challenging because of complex nonlinear interaction between the covariates. And if you think about methods like stratification and matching that we covered earlier, they don't scale so well because the curse of dimensionality kicks in. And what that means is that in case of matching, for example, uh, you would encounter problems of sparsity because the notion of nearest neighbors kind of breaks apart, and you would need exponentially more data points to be able to do that estimation well. Similarly, in case of IPW, the propensity uh, estimation itself gets more challenging in higher dimensions because you would find fewer and fewer number of units as the dimensions scale. As a result, the model predictions might tend more towards 0 or 1, which would blow up the IPW weights. Uh, Recall that we take the inverse of the propensity score as the weights in the IPW technique. So um, if the propensity score tends towards 0, then the weights blow up and we get very noisy estimates. So in all of these scenarios, machine learning proves to be quite helpful because it is able to capture complex nonlinear relationships. It is not constrained by any parametric uh, um, modeling estimate assumptions. And um, in this section, we will cover many of the different modeling approaches that uh, rely on the meta learner framework. So in this framework, what we do is that we estimate the conditional average treatment effects by using your usual supervised learning ML models. And the choice of the model itself is up to the user. Like you can use random forest, gradient boosting, or regularized linear models. And because we are not specifying the functional form and keeping the modeling as flexible, these methods are able to adjust to the data. So let's look at the first of the meta-learner models, which is called an S-learner. So here we are training one ML model to predict the outcomes from the data that we have. Here we take the covariates as the features or the independent variables and the outcomes as the dependent variable. And additionally, we also add the treatment indicator as a feature to train this model. And once this model is trained to identify to identify the conditional average treatment effects, we then get the predictions from the model when we set t equal to 1 versus when we set t equal to 0. And the difference between them is then the gate. So this is a simple modeling approach that pools all the data that we have. But one weakness of this approach is that the model is optimizing for predictive accuracy, which is how well it is able to predict the outcomes given the covariates. And in this prediction, the treatment variable may not be so relevant. And if you are regularizing the model, then then the weights of the treatment or the feature importance may be quite low. As a result, When you consider this equation, setting the treatment as t equal to 1 versus t equal to 0 will not change the prediction much, and thus your Kate would be biased towards 0. So one call out here is that we are optimizing the model for predictive accuracy, but that leads to regularization bias and uh, impacts the estimation of Kate itself. So after the S learner, let's look model, which is called a T learner. So in a T learner, we estimate two ML models. One is trained on the treated population and the other is trained on the control population. This segregation uh, helps to model each of the treatments independently and flexibly. And it also helps to avoid the problem that we saw in the S learner, which is of the treatment getting washed out because of regularization and the Kate estimates getting biased towards 0. But here what happens instead is that uh, because we are training two separate models on different subsets of the data, there is no information sharing between the models. And secondly, in case the treatment assignment is imbalanced, which is to say, for example, if there are far more control units than treated units, then the models will need to be regularized differently to avoid overfitting and um, get good predictive accuracy. But then this difference in how the arms are getting regularized leads to noisy estimation of gate and causes regularization bias. So the next model, which is the X learner, builds on top of the deficiencies of the S learner and the T learner. And here, rather than estimating the gate directly, what we follow a two-step process and impute the missing counterfactuals for every individual. And then from the missing counterfactuals, we generate treated individual treatment effects, and then use those to train a separate model which directly predicts the conditional average treatment effects. So let's take a look at this in detail. So the first stage is very similar to a T-learner approach, where we train two separate ML models to predict the outcomes using control data as well as treated data. In the next step, what we do is we impute the individual treatment effects. So, for example, if you have the treated population, you already know their observed outcomes, but you don't know their counterfactual, which is what would have happened if they were assigned to the control group. So, as an estimate, you use the model predictions from this model and get the individual treatment effect. Similarly, on the control data, you already observe uh, the outcomes when the unit is assigned to the control group, but you don't know what would have happened if they were assigned to the treatment group. So here, since the counterfactual is unknown, uh, we take the prediction from the treated model, like the model which is trained to predict the outcomes from treated data and get the individual treatment effects. So essentially what we have are these D1 and D0 individual treatment effects. And then we train separate models, regression models, using this data. So essentially use the covariates as the features and D1 as the target to build tau1x model and covariates of the controls as the features and T0 as the target prediction label and train T0x model. And then we combine the predictions from both these models to get a blended estimate of the conditional average treatment effect, like so. And this blending is done based on the propensity weights. So here the propensity is measuring what is the likelihood of treatment assignment. So if you're wondering how can something like this help, so let's reason about that. So in case of imbalance, for example, if probability of treatment assignment is much low for a unit, which is to say that E of X is low, then the Kate estimate relies heavily on this part of the equation rather than this part of the equation. And what that means is that this is a more reliable estimate because tau 1 of X is, if you look at tau 1 of X, it is that model is being learned on observed outcomes and predictions from the mu naught model. And since the treatment assignment rate is lower, the propensity score is low. That means that in the control group, we have more samples and more data to estimate this more reliably, which means that we are arcade estimates are relying more heavily on data where we have more confidence. So that's the idea here. And if you think about it, in T-learner, uh, we were effectively using only half the, effectively using only um, split of samples to generate the treatment effects. But here we are reusing all of our data because um, not only are we using our control data, we are also using the model trained on the treated data uh, to learn our final model. So in that sense, there is better reuse of data happening here, and it is also able to uh, weigh on the arms depending on how much confidence we have, and kind of eliminate the issue of T-learner that we saw. Okay. Next, we go on to discuss causal trees and forests. In causal trees, so in supervised learning, you would have come across CART. You would have studied decision trees and random forests, which is an ensemble over those trees. And the idea in decision trees is that we want to recursively partition the feature space so that we can um partition units into subspaces which are similar, which share similar outcomes. And the idea in decision causal trees is similar that, but now instead of predicting the outcomes the way that we were doing in decision trees, we are now interested in directly estimating tau of X. Okay, so we want to partition the covariate space that instead of predicting the outcomes in each leaf of the decision tree, we are able to directly estimate the treatment effects, and all the units inside each leaf are as homogeneous as possible, and across leaves they are different. And inside each leaf, then suppose you have units which are falling in both the treatment and the control group, you would take the average um, of the treated response and the control response and take a difference, and that would be the estimate of tau. And how do you build these trees? So the splitting, so at each split criteria, the splitting criteria is that we want to maximize the heterogeneity in the estimated treatment effect across the leaves. So essentially, we want to choose splits that would, we greedily choose splits that would maximize the treatment effect heterogeneity between the child nodes. This is mentioned over here. That we want. So this is one way of measuring that heterogeneity, that not only do we want the treatment effects between the left child and the right child to be as far apart as possible, we also want to make sure that the size of the split leads to, it's a balanced split. It's not that, the left child has, for example, 90% of data going, and 95% of data is going to the left child, and only 5% of the data is going to the right child. We don't want that. We want them to be balanced and at the same time having as much treatment heterogeneity as possible. And the second thing about building these trees, second, which is distinct from how we build decision trees, is that we do something known as honest estimation, which is to say that whatever data we have, we divide it into two two samples. The first sample is used to decide the splits of the tree and to build the tree. And it's not used for anything else. It's just used for building the tree. And the second sample is then used to estimate the treatment effects. So once you've identified the splitting points, then in each leaf you would use the different samples, the estimation sample to estimate these treatment effects. So this technique is quite neat because it leads to unbiased estimation of the treatment effects. And um, one interesting quality about these trees is that because of this kind of unbiased estimation, we are not overfitting. Uh, uh, it leads to unbiased estimation, and we can construct and it's possible to even construct valid confidence intervals of the treatment effect from this method. We are splitting the data, then the trees that you build will have higher variance. So to control the variance, you would combine multiple trees, take an ensemble by taking an average of across trees. You would estimate. So for a given data point, you would look at the treatment effect estimated by across different trees and take an average over it. And the forest the forests which are grown is similar to how we grow in random forests, where we do random subsampling of the data to grow each tree to ensure that the trees are be correlated. And we also do random feature subset selection at each split, similar to how it's done in random forests. So this method is quite uh, useful. It's well known, well regarded in the industry because it is also interpretable in some sense, and it yields valid confidence intervals. And yeah, so there are some extensions to this method as well that we are not discussing right now, that makes them even better, wherein we call them orthogonal forests, where we generate residuals. And we're going to look at it in the upcoming section on orthogonal learners. But the idea is essentially that we can make them even better, um, and kind of residualize them, um, so that then errors in the model errors do not leak into estimation of gate. So here's a question. Suppose we are building a causal tree, and we have two variables shown here that we can split on. The first variable, and the idea is that we are building a tree to decide whether or not a discount coupon will improve customer purchases. So suppose we consider two candidate splits to grow the tree, then which split would the causal tree favor? So the first variable is called weeks since last purchase. So if the weeks since last purchase is more than 4, it seems that the gate estimate is higher compared to if weeks since last purchase is less than 4 weeks. And on split B, we have splitting by the customer's device, whether it's mobile or web. And based on that, we're able to see these effects. So take a pause and let us and think about what do you think would be a better split for the tree. So I'm sure you guessed it right, that the first split is the one that would be favored because it leads to um, more heterogeneous, splits. And here, if you see, the 4.8 and 5.2 are not that heterogeneous. So this split would be preferred. Okay. Now we are going to look at deep learning methods for causal inference. So we are in a similar setting as before, that we have observational data and we want to not just sometimes infer treatment effects, we are also interested in inferring the counterfactuals themselves. And we want to know, would the patient have lower blood sugar had they received a different medication? Or, other questions like, would the user have clicked on a button if it was a different color, for example? And we've already talked about this, that real world problems involve high dimensional inputs, and modeling the outcomes can get tricky because the outcome response can be very complex. So that's when neural network methods shine, because they're also extremely flexible and low bias function approximators capable of learning very complex and nonlinear treatment response functions. And um, another another feature of these methods is that they can learn useful representations, latent representations automatically, like you don't need to do any kind of feature engineering, and extend that. And they can operate over multiple modalities of data, not just tabular data. If you were doing causal inference on even other modalities of data like graphs, sequential data, text data, etc., neural network methods can be used. So that's the motivation for turning to deep learning based methods. So, so far, the methods that we have seen are using different techniques to kind of adjust for confounding, or ensure that the treatment and the control population are as close, as similar as possible, so that we are able to we are as close to the randomized control trial setting as possible, and we are able to estimate the causal effects. So in this setting, neural network setting, the idea for handling confounding is to do representation learning. So how it works is that um, we want to learn a new feature space, such that the bias between the treatment selection can be removed. So essentially, what we have seen is that uh, in observational data sets, we have confounders, and confounders impact both the treatment assignment probability as well as the outcomes. And what this means and how this manifests is that probability of the X distribution, the covariate distributions for treated and the control groups will be dissimilar. And this is also known as covariate imbalance. And how these methods work is that they try to bring these distributions as close and similar as try to make these distributions as similar as possible, um, so that when you're training models, they are able to generalize. So you're training models on the factual data, right? The observed data, which is the factual data, but you want to be able to infer on the counterfactuals questions, right? The counterfactual distributions. So if these distributions are as similar as possible, then the counterfactual predictions is possible, because we are saying that the model will be able to generalize, right, to the counterfactual domain. So essentially, what we're doing is we're trying to learn a functional mapping file or a feature space, which projects the original feature, the input feature space into phi of x, where the treated and the control populations are representations are difficult to distinguish. So now these are similar. And once this is achieved, then we can essentially have like the meta learner setting, that you can generate predictions for the treatment group. You can set the treatment as 1 and set the treatment as 0, and generate predictions from the model and take the difference as the uh, conditional average treatment effect, as shown here. So the earliest of the model of these models is TARNet, which was introduced by these folks in 2017. So the model consists of MLP layers or any neural network layers. Uh, there is a shared head, there is a shared trunk that is common to both treatments, where the model is learning common representations. And then these representations are being passed to the treatment prediction head and the control prediction head. Um, and for model training, what we do is that we take our observational data and pass it through this model and try to minimize the factual in case of regression, uh, in case where your outcomes are continuous, we frame this as a regression problem and minimize the factual MSE, mean squared errors. So it's written here. So if it's a treated unit, T will be equal to 1, and this term will apply, and this term will go to 0. And similarly, if it's a control unit, then this term will be 0, and this term will apply. So we want to minimize the errors. Uh, we want to train these models, H0 and H1, to be predictive of outcomes. And from that, we are saying, and at the same time, because there is a shared representation that is being used by both models, the idea is that if both models have to perform well, then these representations have to be meaningful and be able to generalize on both sides of the arms. And um, uh, we are able to like balance the treated and control groups. And if the model is able to predict well on this task, then the learned representations would have been balanced and aligned. So it's not an explicit alignment, it's an implicit alignment. We are only training on the factual MSE, and the hope is that um, to perform both these tasks well, the model would have learned, um, meaningful representations, uh, such that uh, you cannot distinguish which treatment. Um, so basically, you want to learn representations that are balanced, which is what we mentioned here, that it becomes difficult for us to predict whether the representation was generated by a treated unit or a control unit. And at the same time, we want the representation to be rich enough to be able to predict the outcomes. Moving on, we look at CFR-net. So this is an extension of the previous model TARNet by the same authors, where now they've introduced an explicit term to guide the learned representations to be as close as possible. So and this is done using an IPM penalty. IPM stands for Integral Probability Metric, which is a family of distribution distance measures over probability distributions. So we are computing. So here we are not computing the distance in the phi of x space. We are computing the distances over the probability distribution of phi of x given t equal to 1 and phi of x given t equal to 0. And one such measure to do this is MMD, which stands for maximal marginal distance. And we are not going to go into details of how exactly it works, but at a high level, MMD is a measure of kernel distance. So basically, it projects uh, this probability distribution into a kernel space, both these probability distributions into a kernel space. And in that kernel space, we take the difference in the means. So difference in the means in the kernel space is equivalent to taking a distance between the probability distributions in the representation space. So that's the idea with MMD. And if MMD is 0, then that means that the distributions are are aligned and overlapping. And the other metric that we can use is also Wasserstein distance, which some of you would have encountered while studying generative adversarial networks. So it is also a distance metric which tries to um, um, look at what is the probability mass that we would need to transport if you had to convert one distribution to another. Okay, so because we are explicitly trying to make the distributions similar in this case, and so the loss function is essentially the factual loss that we saw before, as well as explicit penalty, which is forcing the guiding the representations to be as similar as possible. And the authors also showed here that the errors in the counterfactual predictions is bounded by the factual error and the representation discrepancy. So if your learned distributions are as close as possible, and the counterfactual error will be much lower. Okay. Let's move on to the next section and discuss orthogonal causal ML. In this section, we are going to introduce the double ML framework. So far, we have already seen how ML methods can work in the presence of high-dimensional covariates to estimate the treatment effects. For example, we saw meta-learners, representation in learning methods, etc., that use flexible ML models to fit the outcome regression models or the propensity scores. Note that these models, the outcome regression model or the propensity score model, are called the nuisance functions because they are not of direct interest. They're just like an intermediate step towards the treatment effects that we finally want to estimate. So we also discussed in the meta-learner section that ML models are optimized for predictive accuracy and not for treatment effect estimation. And to optimize for predictive accuracy, these models incorporate regularization. This regularization can be in the form of um, dropout, early stopping, pruning of the trees, etc. But if it's done incorrectly, then the regularization leads to biased estimates estimates, and this bias then propagates to the treatment effect estimation. And even worse is that the bias does not eliminate even if we increase the number of samples used to train the model. So if you see the figure on the right here, we are plotting the sampling distribution of the treatment effects. Actually, no, we are essentially plotting the errors in the sample estimates with respect to the true treatment effect. The black line indicates the zero error line. And if you use naive ML models as your nuisance function estimates to get the gate or the treatment effects, then you would get some, like the sampling distribution might look something like this, which is the orange curve. If you notice here, the mean of the curve is far away from the zero line, which means that the learned distribution is biased. And even if you increase the size of the sample, um, the variance of the estimates reduces. We get much less wider intervals, much less spread across the mean value, but it's still not converging towards the zero error line. So ideally, we want this blue curve, but because of the regularization bias introduced by bias nuisance functions, we end up somewhere here. And because of this, we cannot construct confidence intervals of the causal effects. So the DML framework was introduced in 2018, and it proved to be a very influential development in the field of modern causal inference because it combined ideas from machine learning and econometrics and allowed us to use virtually any ML algorithm for nuisance function estimation, while also ensuring that the learned treatment effects were consistent, unbiased, and you could construct valid confidence intervals out of it. And after this framework was introduced, many other models and modeling frameworks were introduced. For example, the R-learner, D-learner, orthogonal random forest, etc., which build on top of this. So the DML framework introduces three key ideas. First idea is the idea of partitioning out
where we first remove the predictable components of the treatment and outcomes by estimating the nuisance functions. The second idea is the idea of Neven orthogonalization, which addresses regularization bias. So the goal here is to construct and learn the treatment effects so that the errors in the nuisance function estimation do not propagate uh, uh, to the tau estimation. And the third idea is that of cross-fitting, which is essentially controlling for the overfitting bias um, that can creep in if we are overfitting the nuisance functions. And using the same data for training the models, that is the nuisance functions, as well as estimating the treatment effects. So let's look at each of these ideas in more detail in the upcoming slides. Let's look at the first idea introduced by DML, which is that of partialing out. So this idea comes from Robinson's decomposition, which was introduced for kernel regressions. DML extends it to ML nuisance estimation. So we consider the partially linear model where we express the outcomes in terms of a structural equation, which is a function of the treatment and the covariates. So here, our parameter of interest is tau, which is the treatment effect. It depends linearly on t. And outcomes are also driven by a non-parametric form of the covariates, which is unknown to us. And we also have that the errors are uncorrelated with the treatment and the covariates. Now, to estimate tau, we need to do something about this term, which is unknown to us. So Robinson's decomposition has this trick which says that we can take a conditional expectation over this structural equation. So then expected value of y given x is expressed in terms of m of x. Expected value of t given x is written as e of x, which is the propensity score function. G of x remains as is, and this term epsilon goes to 0. And if you subtract both equations and further define y minus m of x as by tilde and t minus e of x as t tilde, then you can rewrite the difference in this form. So essentially now what you have that the residual version of y is now just a function of the residual version of the treatment. And this kind of formulation is useful because it completely eliminates the g of x term. And now if you want to recover tau, you can directly run a regression model to predict regression model and get this, right? So if you recall from the OLS method of regression, one way to solve for the regression coefficients is to solve the normal equation, in which case we have a closed form expression, which is this, which says that the errors are uncorrelated with the independent variables. And if we can find the coefficients which would make this condition go to 0, then we have identified the correct regression coefficients. So the same thing can be expressed in terms of this score function, and we rewrite this here. So epsilon here is nothing but y tilde minus t of t tilde times the treatment, the t tilde term. And if you solve for this equation, which is you set this to 0 and you identify tau from that, you essentially have done a residual on residual regression. So if, in case you're wondering why such a setup might be helpful, then let's talk about that. So essentially, if you think of the causal graph that we studied in part 1, you would know that the confounders impact both the treatment as well as the outcomes. And this kind of a setup where we have a model which predicts the outcomes from the covariates or the confounders, and a model which predicts the treatment from the covariates, is sort of adjusting for the impact of the confounders. And what we are left with is now everything that is not explainable by the confounders. So essentially, you can think of it as sort of eliminating the impact of the backdoor path from the treatment to the outcomes. And now whatever relationship exists between T tilde, the residual versions of the treatment, and the outcomes is the direct causal effect. So this is why it's a neat idea. And how DML extends this PLM model is that now instead of now for the estimation of M of X and E of X, we can use ML models. So second idea that DML introduces is that of Neyman orthogonality.
So in the last slide, we saw that Robinson decomposition allows us to estimate tau by running a regression on the residuals uh, T tilde and Y tilde. The same can also be estimated by creating a score function and identifying the tau values, which would set this score function to 0. Now, this idea is extended to Neyman orthogonality. So essentially, what we have now is a score function which we want to set to 0. And the values of tau, which would allow us to do that, are what we are interested in. But in case, but you see that the score function is also parameterized by the parameters of the nuisance models, which are denoted here. And in case we are making errors in the nuisance estimation, then this tends to bias the estimation of the score function as well, and we cannot recover tau correctly. So the goal is to create a score function such that it is insensitive to first order errors in the nuisance functions. So essentially, if this derivative condition is satisfied, which is saying that the score function still remains 0, even if you take a then goal is that we want to redefine the score function so that it is insensitive to errors in the nuisance functions. And this is expressed in terms of the derivative shown below, right? And if you see the figure on the right, we have plotted the nuisance errors on the x-axis and how they impact the resulting bias in the treatment effect estimation on the y-axis. And we can see that in case we don't have orthogonality, first the errors propagate as a linear function, which can be shown by this orange point. So anytime your errors increase, it linearly impacts um, the treatment effect bias. And in case you have orthogonality, then because of this condition getting satisfied, um, the bias still propagates, but the magnitude of it falls. Like instead of O of delta, we now have the bias proportional to O of delta square. And in fact, it can be shown that the bias is controlled by the product of the two nuisance function errors. This bound allows us then to be able to construct valid confidence intervals and generate nearly unbiased estimates of tau. Let's look at the next idea introduced by the DML framework, which is that of cross-fitting. So if we use the same data to train the nuisance model and then estimate the tau, then we have a problem of overfitting, because then what happens is that the estimation errors become correlated with the outcome residuals, which leads to overfitting. So as a fix, what the cross-fitting approach proposes is to divide the data into k folds. And once we have these k folds, we would compute the residuals uh, only using out of sample nuisance model, cross-fitted nuisance models. So how cross-fitting works is that we divide the data into k folds, and in each fold we train the nuisance models on k minus 1 folds, and then use the model predictions to create the residuals on the held out fold. So this is denoted here. So the outcome model, the propensity models are all fit on the k minus 1 folds. And then when we are generating the residuals, which is y minus prediction from the outcome regression model and t minus prediction from the propensity model, then those predictions are done out of fold. And then we can use the residuals
to train an OLS model, which will give us the tau. So what this approach ensures is that the residuals are now computed on data which is not seen by the nuisance models, which prevents the overfitting problem. Next, we look at R learner, which builds on top of the DML concepts of Robinson's partially out transformation and Neyman orthogonal objectives and uses it to estimate Kate. So the setting here is also the same partially linear structural model, but now instead of tau of x as a constant, we are looking at Kate, which is a function of the covariates tau of x. And the next step is to residualize the outcomes and the treatments like we did in the previous step. And the residuals are computed out of sample, which is to say that they are cross-fitted. And this helps to remove the baseline outcome variation, which can be explained by the confounders or the covariates. So whatever remains is the causal effect. So if there is any relationship between tilde t and tilde y, then we would attribute it to the causal effect because we would say that we have removed the confounding effect by taking the residuals. So once we have computed the residuals, we can express it in terms of this regression equation. Instead of tau, which was a constant in the previous slides, now we have gate, which is a function of x. Okay, and essentially to recover tau of x, we need to run a regression model where the local slope is the gate tau of x. Right, so this can be fit by gradient descent. How do you go about estimating tau of x? You can do it in this form where we have an objective function and then we want to learn a function tau which would minimize sum of squared errors. So unlike OLS, which estimates fixed coefficients, the R learner estimates an entire heterogeneous function.
The next model we want to discuss is a DR learner. So this is a Kate estimation model that is both doubly robust as well as Neyman orthogonal. So if you recall from part 2 of our series where we discussed AIPW, it builds on top of the ideas discussed in AIPW where we model two nuisance functions. One is the propensity model as well as the outcome regression model. And in AIPW, we saw that if either of the models is consistent, then we are confident that even the treatment effect estimation will be consistent, which is to say that as the number of samples increase, the model will converge to the true treatment effect value. So in DR Learner, the idea is to first build the propensity and outcome regression nuisance models. And then for each unit, we then create a doubly robust pseudo outcome. So we can think of it as like a noisy version of the Kate estimate. And the formula on the left uh, illustrates this. So essentially what we are doing is taking a difference in the outcome regression model predictions. And then depending on whether the unit is assigned to the treatment group or the control group, we are taking the residuals and applying a propensity weighted correction. So if you look at these terms, it should be familiar because we have discussed the same in the AIPW slide. Essentially, this portion of the equation is whatever is applying, you can think of it as applying IPW to the uh, residuals, and this can be thought of as the modeling the gate from the outcome regression models. So once we have the pseudo outcomes generated for each unit, we can now treat them as regression targets. So essentially, what we have is that we want to model, we want to train another model and regress those pseudo outcomes on X. And we can use any ML model to get that. So learn a model that will be able to predict these noisy K targets using the covariates, and that would give us the treatment effects. So this approach actually works quite well in practice, and it has two desirable properties: double robustness which is to say that if either of the models is correctly specified and consistent, then the Kate estimates are also consistent. And secondly, it is also Neyman orthogonal, which means that if there are errors in the nuisance estimates, then those errors only propagate to the Kate estimates at a second order. We've now come to the end of the topics for today's discussion. We've seen multiple ML approaches for Kate estimation. Let's now summarize what we have studied so far. I know we've covered a lot of approaches, and let's just visually see how these approaches map out. So consider this canonical causal graph that we introduced in part one of this series, where we said that we have confounders that are impacting both the treatment assignment as well as the outcomes, and that's what makes the effect, and that's what makes the estimation of the treatment effects, which is the influence of T from Y, difficult to estimate. And if you don't do any kind of adjustment, then the estimated treatment effects are biased. So essentially, what we want is that we want to remove the causal influence of these edges, which are part of the backdoor path, and the different methods handle this in different ways. So let's take a look. So in randomized trial, if you recall that treatment assignment itself is randomized, which means that treatment assignment no longer depends on the confounders. And essentially, we can think of it as kind of removing this edge. And because if this edge is removed, then we no longer have this backdoor path through which causal influence is flowing, and we can directly estimate uh, the treatment effects from the treatment arm to the outcome arm without any adjustment. And this is the reason why randomized trials are considered the gold standard for causal inference. Next, we look at matching or stratification. Here we said that we will condition on the covariates and create multiple strata. And in each strata, we can see that the treated and the control units are now similar, and we can estimate the causal effect. And this happens because conditioning on X blocks this causal pathway, if you recall from our discussion in part one. This approach works in low dimensions, but as we move to higher dimensions, then matching and stratification uh, gets challenging because we have fewer and fewer units to match on as we run into the curse of dimensionality. So if we look at propensity-based methods, the idea is that we want to model the propensity and then reweigh the units to build a balanced pseudo population in which the treatment no longer depends on X. So essentially, what we are saying, if there are units which have a much higher chance of being assigned to the treatment, we want to reduce their weights. And similarly, we want to upsample those units which have a lower chance of treatment assignment. And this helps to balance the population. And now in the pseudo population, we assume that the treated and the control groups are similar, and therefore we can estimate the causal effect. Next, we looked at meta-learners, where the idea is to model this arm, which is the influence of the confounders on the outcomes. And we regress y on x and t, and conditioning on x blocks the confounding. So we have seen S learners where we fit one model with treatment as a feature, and we saw T learner where we fit two models. Next, we looked at meta learners, where the idea is to model this edge, which is the causal influence of um, the confounders on the outcomes. And doing so, we condition on X, which blocks the backdoor path and enables the estimation of treatment effects. And we saw multiple such models. For example, the S learner, where we fit one model with treatment as a feature, and T learner, where we have separate models per treatment. And these models are simple and flexible, but of course, we also saw that um, they suffer from regularization bias. Next, we looked at doubly robust methods. So here the idea is that we want to model both uh, these edges and fit these nuisance models, the propensity model and the outcome regression model. And The cool property about doubly robust methods is that if either of the models is consistent um, and specified properly, then we are sure that even the effect, even the treatment effects estimated would be consistent. So examples of doubly robust approaches that we saw included AIPW and DR Learner. Next, we looked at double machine learning. So here the idea is that we estimate the causal effects on the residualized treatments and the residualized outcomes. And in the residualized versions of the treatment and the outcomes, the backdoor part doesn't play a role because we have removed its effect. And this happens because when creating the residuals, we are removing the influence of the predictable influence of covariates on the treatment and the predictable influence of covariates on the outcomes. And in a way, we are saying that we have kind of eliminated the influence of these edges. And now, whatever we are left with is the true causal effect between T and Y. Next, we've just compiled the list of HTE estimators that we've looked today. What are the main objectives and what properties do they exhibit, whether they are Neyman orthogonal, doubly robust, and capable of handling imbalance treatment. So this is just for reference. So in the today's presentation, we mainly focused on the different causal ML methods that exist. But beyond just treatment effect estimation, causal ML and causal inference uh, thinking is being used across multiple domains. And let's just take a quick look over that. So one area where causal ML is being used is in robust and generalizable ML. So if you look at the example here, this is a well-known failure case of supervised learning where the model is trained to like an image detection model trained to identify uh, trained to identify objects in this image is not able to detect cows uh, because of distribution mismatch between the training set and the testing set. So in the training set, most of the images of cows were against backgrounds of grassy lands, whereas the images in the test set were pretty out of sample for the model, and therefore it's not able to generalize. As humans, we are obviously able to generalize this, but the model is learning to identify cows based on spurious correlations, and this is not what we want. So the idea in robust and generalizable ML is that we want to learn causal relationships that stay stable under these kind of distribution shifts and not influenced by spurious correlations. Okay, so traditional supervised learning assumes that the training and test data come from the same distribution, and if that's not the case, then we see failure cases, and it's quite. And in reality, it happens pretty often. It's not environments do change, so it's not an unreasonable expectation to have the training and the test time distribution to always match. So here we are in this paradigm, we are trying to learn invariant features such that we are able to identify the cow by looking at cow itself and not basing our predictions based on spurious correlations based on pixels such as the grassy lands. Next, we're going to look at causal uh, generative modeling. So generative AI is also becoming causal. Instead of simply sampling images from a learned distribution, causal generative models ask questions like, what would this MRI look like if the patient did not have this disease? And how would this face change if the age of the person increased and if everything else remained fixed? So we are trying to kind of disentangle the spurious, again, disentangle and find the true causal drivers of, you know, uh, base our predictions on spurious correlations. And this kind of paradigm is useful for controllable diffusions, for counterfactual data augmentation, and simulations and all kind of generative use cases. Um, Next, we're going to look at causal RL. So here, there are multiple applications of causal inference in the RL paradigm. So one such application is dynamic treatment regimes. So far, we have looked at, the impact of intervening on one variable at a time. And in real life, you would have, sequences of treatments being taken. For example, in case of, patients undergoing treatments, there would be uh, if you consider the drug as the treatment, then the drug dosage itself changes over time, and depending on how the dosage is titrated, you might see different outcomes. And if you're interested in learning the intervention dynamics instead of like purely observational transitions, then you need to incorporate causal thinking. Another area is causal bandits. So they they exploit the structure to predict outcomes in the interventions. And then model-based RL and world models are another area where causal methods are being used to learn the environment dynamics. Uh, so many of the causal techniques like doubly robust score estimation, orthogonalization, etc., are being used to solve RL problems. And we also see that in off-policy evaluation, which is a fairly common setting in RL, causal um, techniques to address confounding and policy effects. And again, in counterfactual credit assignment, we're trying to learn which actions truly cause the reward. You're taking multiple actions to optimize some long-term reward, but if you want to determine which particular action truly caused the reward, then counterfactual credit assignment is one area of work. Next, we're going to look at fairness and explainability. So, I'm sure you would have come across this that we are already aware that ML methods are being increasingly used to assist in life-changing decisions like, you know, sentencing, parole sentencings, loan applications, university admissions, and so on. And these decisions can have like ethical and legal implications. So, model practitioners obviously have to be very mindful of the societal impact of their work. And fairness is a lot of work is being done on fairness, and it is increasingly be defined in causal terms. So counterfactual fairness is a way of asking whether a model's prediction would stay the same if a person's race or gender was different, while everything else remained constant. So this provides a much stronger notion of fairness than simply comparing demographic level statistics, because we are truly isolating on the intervening variable that if all else remains same and we only change the gender or the demography of the person or the race, would the model predictions change? And again, it's being used in explainability as well. Like we need to be able to explain uh, the notion of why certain model actions were being taken, what were the driving variables. So even for that, causal inference is being leveraged. And then in LLMs, uh, first application, like there are obviously multiple applications, but first application that comes to mind is to be able to automatically extract causal knowledge from massive scientific literature. You have a lot of scientific literature available to you. How do you parse through that literature and build causal graphs that can help accelerate scientific research? And then again, there's a lot of work being done on LLMs to study LLMs and see if their responses are actually driven purely by statistical associations and hallucinations, or whether they're actually able to uh, reason about interventions and counterfactuals. So, yeah, so this is the talk. And with this, we've come to the end of this talk. Hope you folks had some good takeaways and you were able to understand and appreciate the field of causal inference and why it's relevant. And it's relevant not just for industry applications, industry or research applications. Uh, I believe that having this kind of framework in mind is helpful in real life as well. Because in real life, we are also presented with a lot of information, and having these concepts in mind helps us disentangle what truly is driven by causal effects versus what is purely observational. Like if if you're reading news articles or there are politicians making claims, it makes you a better informed citizen to be able to just uh, critically examine the data that is being presented to you and um, yeah, be better citizens, I suppose. All right, with that, we've come to the end of this talk. Thank you